Let me share a little bit about my own work and how I'm using evolution right now. There is a virus which is known to be present in a large percentage of prostate cancer cells, called XMRV. It's not known yet if it has a causative role, but its presence in a high percentage of prostate tumor biopsies is an exciting discovery and has the potential for very early diagnostics, and possibly even a highly effective treatment for the millions of men, like my father, who have prostate cancer. Now, the virus has been sequenced and studied, but the best information we have about it we have gained from a study of its closest relative, a mouse endogenous retrovirus I will simply call MERV. A study of MERV has shown us where the key genes are located in XMRV, and the diagnostic kits for XMRV are simply designed to detect the MERV, which acts as a positive control. Without the conceptual framework of common descent, we would have no basis for such assumptions. I can safely say I use evolution on a daily basis to develop diagnostics and therapeutics. So has comparative genomics and macroevolution produced some useful innovations? Absolutely, both directly in the form of tests and drugs, and indirectly by shining light on difficult problems of genomics. Section 7. Understanding the past. Evolution also gives us a contextual basis for our place in the natural history of this planet. It gives us the power to develop models about the events of the distant past. Reading genetic phylogenies is a bit like reconstructing a family history by looking at a group of distant cousins and arriving at likely conclusions about their common ancestor. This may be the most esoteric of the applications, but I think that evolution tells us a great deal about the process and purpose of life. It explains some of the behaviors that we observe. It explains, for example, why we find baby animals so adorable, why we smile, why we are a mostly monogamous species. And it does so in a way that is more satisfying than religious creation mythologies, because the evidence is empirical and objective. Macroevolutionary genetics are also an important line of evidence to add to the whole picture of the distant past, matching it up with similar information from biogeography, geology, ice cores, fossil evidence, and stratigraphy give us additional confirmation, or reveals interesting puzzles to be solved. Understanding the cataclysmic events that may have happened in the past, such as the extinction of the dinosaurs, makes us more aware of the risks we face now, such as meteor impacts, climate changes, and pandemic disease. We fully understand that survival on this planet is a fragile thing, and we have the perspective to understand that almost all of the living things that came before us are now extinct. Section 8. Beyond Biology. In addition to helping us understand living things, evolution has also proven to be a productive framework outside of the study of biology. Genetic algorithms are used to design cars, industrial controls. They are indispensable to such projects as space exploration and national defense. Genetic algorithms control the heaters on the space shuttle. They help mathematicians solve complex problems. They even get used in search engines and database structures. Tools developed for evolution of biological systems have also proven useful in the study of other evolving things. The evolution of language, for example, can be placed on phylograms. Divergence rates can be calculated, and simulations based on biological evolution have been quite productive in the evolution of language and cultural traditions. For example, we can learn about the cultures of an ancient people by understanding which words they adopted from neighboring groups, which words they invented, and which they stopped using. All this evidence helps us to build an understanding of human history and linguistics. Directed evolution is a process of chemical and biological selection to optimize the function of a bioengineered system more quickly than manual design optimization. Suppose we have a large library of chemicals that we are screening for potential to bind to immune cells and turn off a particular pathway. This is called a compound library screen, and for this case the potential might be to stop the progression of multiple sclerosis. Now suppose we have a few million compounds to look at. The brute force approach would be to go through each of them one by one and see if they have any effect. This would take hundreds of millions of dollars and several years' worth of work for a large research team. But if we instead took 1,000 root molecules and screened them, Then take the best 10 and create sub-libraries of new chemicals from those parents, and screen the children compounds, each time taking the most successful and using them to create further diversifications. We will find our optimal drug design in a much shorter time and for less cost. The same process can be used for the production of proteins, like antibodies or vaccines, but the diversification process is the introduction of mutation or recombination by chemical or enzymatic means. This process is how most commercial antibodies are developed today. It turns out the natural process of genetic evolution is faster and easier than the scientist as intelligent designer when it comes to drugs and bioengineered proteins. Section 9. Conclusion. Theodore Dobzhansky is well known for the quote, "Nothing in biology makes sense except in the light of evolution." Dobzhansky was a Ukrainian biologist who, in 1937, wrote one of the seminal works of the modern evolutionary synthesis, Genetics and the Origin of Species. He studied at Columbia with T.H. Morgan, the scientist whose name is now used as a measure of recombination distances, usually as measured in centimorgans. Dobzhansky was a critic of anti-evolutionists, as we might expect as one of evolution's greatest champions. But he was also a devout member of the Eastern Orthodox Christian Church. He believed in a God that was more than a deceptive tinkerer, one that was compatible with observed evidence. I'm going to include a link to the original 1973 essay in the sidebar. But I want to briefly introduce one of his students, Francisco Ayala, a National Medal of Science winning scientist who uses evolution to study tropical diseases that affect more than 20 million people a year. Francisco is a former Dominican priest and devout Catholic. He is also one of the most prolific and well-respected authors of the modern age in the field of evolutionary biology, with 950 publications and 30 books. His debate with William Lane Craig is available here on YouTube and worth watching. What I'm trying to say here is that this is not and never has been between Christian faith and evolution. It is between science and anti-science. The body of scientific knowledge of the last 2 centuries versus the radical views of a handful of scriptural fundamentalists. There is no way to know for sure what effect teaching creationism in our schools would have, but we can certainly look to the more fundamentalist Islamic countries as an analogy. Are they better off under a theocratic educational system, or worse? Are we willing to trade off all the benefits I've covered in this video? Beyond that, are we willing to set a precedent for future scientists that politics and ideology trump evidence and investigation? I'd like to end with a quote from Dr. Ayala, a man of faith and science. American children are consistently falling behind those of other nations in their knowledge and understanding of science. We will not be able to close this gap if we substitute ideology for fact in our science classrooms. Thanks for watching.